Hello friends, welcome to the online course Digital Design using Verilog for absolute beginners. In today's lecture, we will try to understand the Verilog behavioral model. Let us first understand what is this Verilog behavioral model. What do you mean by this behavioral model? In our earlier lectures, we have seen that to design a digital system, a Verilog designer can use various types of abstraction levels, various types of design models. You have seen earlier a gate level model, switch level model, data flow model, etc. Among these models, this behavioral model is one of the topmost models. It is considered as the most suitable model for an efficient designer, and it gives a lot of scope to design any complex digital system. Let us try to understand the details of this behavioral model with an introduction. This model is considered as the highest level of abstraction in the Verilog design modeling methods. It is also popularly known as procedural assignment. Verilog behavioral model procedural statements control the simulation and manipulate the variables of the data types. So what is the use of these procedural statements? They will control the simulation and manipulate the variables of the data types. Various data types which you have studied earlier, they are used to describe the system, digital system. So this behavioral model provides a wide scope for the designer to build any complex design which can be properly simulated and synthesized. The statements that we see in the behavioral model, normally they are known as procedural statements or procedural blocks. That means each block is associated with certain number of statements. So what we say is the procedural block of Verilog HDL is defined as a region of code containing sequential statements. Normally, there are two types of procedural blocks. One is the always block, the other is initial block. Each initial construct and each always construct starts a separate activity flow. These always block and initial block are also known as Verilog constructs. What they actually do, they will provide a separate activity flow. All of the activity flows are concurrent to model the inherent concurrence system. So what we do here, the procedural assignments which we make, they are executed concurrently. Let us try to understand some more details. The procedural assignments are used for updating reg, register, integer, time, real time, and memory data types. There is a significant difference between the procedural assignments and continuous assignments, because we have already seen in our earlier lectures. In the data flow model, we use continuous assignments. That is the basic difference between data flow model and the behavioral model. In the behavioral model, we use procedural assignments, whereas in the case of data flow model, we use continuous assignments. Then what is the difference between the two? Continuous assignments drive the nets and are evaluated and updated whenever an input operand changes its value, which we have seen. So whenever the right hand side of an assignment statement changes, then that statement will be executed and the result will be assigned to the LHS, left hand side of the assignment statement. In the procedural assignment, update the value of the variable under the control of the procedural flow constructs. That is the difference that surround them. So this is the basic difference between the continuous assignment and procedural assignment. So as you have said, this earlier slide, this procedural block contains two important constructs. One is always block and the other is initial block. First, let us consider the always block. The always block is a continuous loop that never terminates. This is the most important thing. In any Verilog behavioral model, always block is continuous loop. It will be in a loop. Whereas initial block will be executed only once. We'll come to that point afterwards also. So let us see how this always block looks like and how it helps the designer to design a digital system. So a Verilog module can contain any number of always blocks. This is the most important thing. A Verilog module, as you know, what is the meaning of this module? It's a kind of subsystem in the complex digital system. So if a Verilog module, they can have either one always block or they may have number of always blocks. And remember, all these always blocks are executed concurrently. So let us see the syntax. The basic syntax of always block is always, remember, this is the most important thing, always at the rate, at sensitivity list. That means this sensitivity list, or sometimes people also call an expression. So whenever this sensitivity list, the variables mentioned in this list changes, then only this process starts. That's why I have written here begin, and every begin must be closed by end. So always at, based on this sensitivity list, you do the following. That is begin, statement 1, statement 2, statement 3, statement n. There may be n statements at the last end. So this is the basic format of always block. So always will have at the rate, at sensitivity list. So let us understand with a simple example. So the sequential statements are executed if and if only the signals of the sensitivity list changes. That means these statements are executed only when the variables or the values of the sensitivity list changes or the signals changes. If these things do not change, it won't go further. So let us see with the help of an example. Here I have considered a 2:1 multiplexer. So only to make you to understand, I have shown here A is the input, B is another, 2 inputs, and I will have 1. Only to explain some details, I have chosen Q bar also. Q is the output, Q bar also. That is, complement of Q is also taken. So as usual, module, my mux, name of the module, this is the port list, A, B, S, select pin, as you know already. Q is one input, output, Q bar is another. A, B, S are directions of the ports, input, Q bar are the, and as you know, as usual, the right hand side here, it will be always a register, Q comma Q bar, the outputs, they are taken as registers. And you know, how do we define? Always at A or B or S. That means whenever the inputs either A or B or select pin changes, any one of these, either A or B or S changes, perform this. Else don't perform. People may get a doubt. Suppose there is no change here, so it won't do these things. That is A or B or S, A input or B input or S. At least one of these things, if they change, always do this. Always at A or B or S, start begin. If yes, that means if the select pin is 1. If yes means if it is true. That is the meaning. What is the meaning of true? If yes is equal to 1, then assign A is equal to Q. Output is Q. Else assign B is equal to Q. This is the normal thing which we know. So that means whenever this select pin is 1, assign the value. Whenever this is 0, according to your logic, this will be assigned to this. Based on the value of yes, either A may be assigned or B may be assigned. So that's what I have defined here. B. Yeah, so every begin must be closed by an end statement. But here I have chosen a separate statement also here. Assign q is equal to this. Q is q bar. That is a negative negation of this q. That is q bar. End module. So this is a simple program. Actually, this is procedural descriptions must be there. But to tell you clearly, explain you that this all behavioral model can also contain continuous assignment. That's why these are all procedural descriptions. This is a continuous description or assignment. So assign Q, that is Q bar is assigned to, you can see this here. This assignment is a continuous assignment. So this is how we explain the always block of a behavioral model. So let us take up next the initial block. What is this initial block? The initial block is typically used to write test bench for simulation. It specifies the stimulus to be applied to the design under test or device under test. You can use this. So to test this functioning of this device, we apply some stimulus. I will explain all these things when I make another video on test benches. At present, you can say that the initial block is typically used to write test bench for simulation. So the initial block is executed only once. As I mentioned earlier, the initial block is executed only once at the beginning of the simulation. Once we start the simulation, because the simulation will be performed only once with a given input stimulus. So initial block is always executed once. Let us have another illustration, another example here to understand this initial. So module behave, because there are no input outputs here, it's simply some operation. So A and B are taken as vectors, each is a 2-bit vector. Now initial begin. So A is defined as a 1-bit value, 1-bit size, and whose value is 1. B is defined as again of size 1 bit, whose value is 0. End, we have defined these things. These are useful during the simulation actually. So A and B are defined. Now what we are saying, the behavioral model, always, no condition, nothing. Begin #50. This always indicates, remember, the time delay. We'll understand this in the next classes about this. That means you please perform this. That means negation of A is assigned to A. A is equal to negative of A or negation of A or not of A or complement of A only after 50 time units. Only after 50. This we are introducing the time here. End. So this begin end. Similarly, another, as I have told you, in a module you can have any number of always blocks. Another always block. Again, always begin after 100 time units. Assign complement of B to B. That means B will become B complement. So end, because every begin must be closed by end. Begin end. Similarly, so initial begin end. So this is a kind of input stimulus to the test bench. I will get after every 50 time units. A is inverted, that is complemented. B is complemented after 100. That means those who have a minimum knowledge about this, you can understand that it will give a kind of square pulse. After every 50 time units, A will become complement of A. So here A is 1. When it will become 0, it will become 1. Like this, you get a square pulse. This is a simple generation of a pulse, square pulse. Similarly, so in this model, the reg variables A and B initialize to 1 and 0 respectively, as you have seen at the simulation time 0 at the starting time. And they will be, initial construct is then complete and it does not execute again this simulation run. That's important. Once it is completed, it will not be executed further. Only once it is executed, and this loop will be always blocks will be repeatedly done, repeatedly executed. This is the most important thing. So the values is, as I have explained, this the same thing. So thus the register A inverts after 50 time units and register B inverts the signal after 100 time units. That's what I explained in the earlier slide. So next, let us understand what are the different sequential statements that are used in your always block. That is the most important thing, because in a behavioral modeling, you can use various different sequential statements so that any complex design can be done easily, can be done effectively. So based on the efficiency of the designer or his understanding, he can make the things better. For this purpose, what are the different sequential statements available here? Number one, the simplest is begin. Begin followed by sequential statement N, which we have seen in the earlier. So if you see here in the earlier example, I have shown you here in begin followed by some statements. Similarly, begin these some statements end. So begin followed by some statements. Yeah, simple. So yes, begin followed by some sequential statements end. And remember, if there is a single statement in the block, begin and end need not be required. You can directly write without begin and end also if there is only one statement. If there is a single statement in a block, you need not write. But even if you write, there is nothing wrong. So next one, if followed by expression. We may write if A greater than B. Execute these things, this block of statements. So if expression sequential statement. If A greater than B, Y is equal to Y bar, Y is equal to A, Y is equal to A and B, you perform this. So this is a kind of condition. If expression sequential. Else, if it fails, do this. Else, do this. For example, if A greater than B, Y is equal to 1. Else, Y is equal to 0. Simple example. So like this, you can also use if sequential statement. Next one, case asset. If you recall your C program, some of these things are already available in higher level C language also, but all are not available. We'll see. So this case is also available. Case statement. Case followed by some expression. We'll see. We'll take up an example in the next slide. So for different values of this case, different statements will be executed. So expression 1 is true. Then sequential statement 1. Expression 2, sequential statement 2. Expression n, sequential. If none of these are true, then you ask the compiler to assign the default sequential statement or execute the default sequential statement. So since we have started with the case, it is end case. Another sequential statements that we use. So different sequence. Forever. So forever means it's a continuous loop. Of course, it's not available in C language. So it's only available in Verilog. So forever, that means you do this continuously. Forever you perform this sequential statement. Just like if you see in an assembly language, etc., we write go. That is a kind of unconditional jump. Similar to this, forever you perform this. That means there is no condition, etc. Simply. Another one, repeat, followed by some expression, perform the same sequential statement. For example, repeat 10, repeat 20. That means for 20 times you do this. If you remember your assembly language program, those who are familiar or who remember the 8086 programming language, etc., there we write loop similar to this. Loop 10 times, 15 times, 5 times, 2 times. That similar to this repeat is a kind of loop. Repeat 10. That is, this statement will be executed 10 times. Another construct is while. So while followed by some expression. While this is true, execute this. Otherwise, not necessary. And this is also very familiar to you, for loop. So for expression 1, expression 2, expression 3. Then execute this. Say I minus minus, or for I is equal to 0 to I greater than 5. I plus plus something. So we have 3 expressions here, and based on this, we'll perform this sequential expressions. So this is also our sequential statements. Last one, at event expression. at the rate which we have seen already. So at the rate of some event, you will perform a block of statements. So until this expression is true, and it will suspend the, that means it acts like a trigger pulse. So this makes a block of statements suspend until the event expression triggers, that is until it becomes true and triggers. The below block of statements are not executed, they are suspended. So this is another interesting thing. Now to explain this, let me take an example, the behavioral model, D flip-flop. So as you know, D flip-flop, the data in clock, Q and Q bar. So module, example D flip-flop, what are the inputs here? D and clock are the inputs, Q and Q bar are the outputs. How we, so the direction of the ports input, D and clock are the inputs, Q bar are taken as outputs. So we know that Q and Q bar are register type. The left hand side here, they are register types because they store the value until, that means the D changes or clock changes. How do you represent this? Behavioral model, always block, always at negative of the clock. So whenever the clock is at the negative edge, edge means negative edge of the clock, always at the negative edge of the clock, begin, do the things. What it has to do? Make Q is equal to D, that is assign the T value to Q, that is Q will become the T and Q bar will become complement of the D. So invert of the D. So this is at the clock, at a very negative clock pulse. Do this. Begin must be closed by N and module must be closed by N module. So this is a very simple sequential logic example for your behavioral model where we use always block. So another example, most important, normally students will prefer to use this 4-bit ALU, arithmetic logic unit. We know that in arithmetic logic unit, the arithmetic logic unit will perform various operations. It can be used to perform addition or subtraction or multiplication, exponentiation, so on and so forth. To explain here in a very simple way, I have chosen a 4-bit. The data is of 4-bit and I have chosen 3 or 4 operations. Let us see how we do this, and you can extend this to any number of operations based on the select line. Let us take a simple case, very simple case of 4-bit ALU. So example module, example ALU 4-bit, Y output, A is the input, B is the input, S means select operation, which operation is to be performed, whether it is an AND operation or means addition operation, subtraction operation, multiplication, division, exponentiation, or and so on. So example ALU4, Y, A, B, S. Y is the output, A is the input, B is the input, S is the select line. Now, as I have already told you, what is the direction of the ports? A and B are the inputs, but they are vectors, as I have told you in the earlier data operators. 3 down 0 means it's a 4-bit vector. That means A is a 4-bit vector. It can have the value 0101, 1000, or any value between 0000 to 1111. That's it. B also same. But select is only 2-bit vector. That is 1 down 0 means you can have only 2 bits. That means 0001, 1011. That means I can have 4 operations with the help of this. Suppose I define this here as 2 down 0. That is I will have 2, 1, 0, 3. What are the 3? That means I can have 2 power 3, 8 options, 000 to 111. But as a simple case, I have chosen only a 2-bit vector. And what is the output? Obviously, when A and B are 4-bit, output is also 4-bit. As I have told you in earlier lecture, parameter in the data operator, which is a global constant, I can define here. So I define add is, that is 2-bit value, 00 is assigned to add. Similarly, 01 subtraction, 10 multiplication, 112. We are already defining these things. That means whenever it come across 00, perform the addition. Whenever it is 01, perform subtraction. Whenever 10, perform multiplication. Whenever it is 11, perform division. Now let us see the action. Always at A or B or yes. That means when one of the values, these values changes, that is inputs changes A, B, yes. Once this is called sensitivity list. I have already told you sensitivity list or expression A or B or yes. So case yes, I am choosing the case of yes. So what is this? Add y is equal to a plus. What is this add? That means when it is 0, 0. So when yes is 0, 0, select first one, perform the addition. Similarly, when subtract, when do you perform the subtraction? Y is equal to a minus b. So we have already defined in the global parameter. When it is 0, 1, perform subtraction. When it is 1, 0, perform multiplication. Let us see. So I have written mul, y is equal to a star b. Division, y is equal to a by b. And case, end module. So this is what is known as the simple example for a 4-bit ALU using always block in the behavioral model. So in this simple block in a behavioral model and with some examples. So in the next coming videos, I will try to explain some more concepts of the same behavioral model with some more complicated examples. Thank you for watching. Good luck.